So let's get started by writing some code, some Verilog code specifically to describe that 2-to-1 multiplexer circuit. And I will start by talking about the structure representation. So I'm going to show you a couple of ways to describe the structure of that circuit. So I'm going to just copy that circuit in here so that we can use that diagram when we write our code. And I'm going to tell you that the first method is actually the simplest, which depends on gate level primitives. So these in here are what we call gate level primitives, actually these ones in here. What are they? They're basically the most basic gates you've seen are the AND, NAND, NOR, all of these gates. And if you take a look at the description, for example, let's say we take a look at the NAND, it tells me F equals A, B, C, D, depending on how many signals or how many inputs you want. And what the usage is you're going to say AND, F, that's the output, and then a bunch of inputs, as many inputs as you want. Okay, so let's go to Vivado and write code to describe that particular circuit. So I'm going to go in here. I'm going to put that on the side so that we get to see that. So now I'm here. I'm in the, like you can see that I'm in the hardware manager. In order for me to add a new source, I need to get out of the hardware manager. I'm here. So I usually just click on this little X in here and it just takes me out of it, and that's fine. I'm just going to close it. And once you're done, you will see that you're back to this project summary, or like I'm going to double click and I have the sources. So I have that buffer that I wrote. I'm going to just say, hey, I need another design source this time. It's not a constraint. Pay attention. This is important because it will actually place it in different folders within the project files or directory. So it's a design source. And what I'm going to do is I'm going to say, okay, I'm going to create a new file, and it's a Verilog file, and I will call it, for example, mux 2 times 1 or 2 times 1, okay, and then gate. Okay, so mux 2-to-1 gate level, so representing gate level. I'm going to create several of them, and this is using gate level primitives. So I click OK and I click finish. Of course, I can go ahead and say the inputs and the outputs I have, but I'll just go and write them in the file directly or in the module. Okay, so it's creating that, and you'll see that we have that source in here. So that's the one in here. So I'm going to just double click on it, and I'm just going to double that, and you'll see again, anything in Verilog lives in a module. So I have a module, and then that's the name I gave it. Okay, and that's basically, I'm calling it multiplexer underscore 2 times 1 gate. Gate level stands for gate level modeling, and then there's an end module. And in here, I have to provide it with the input and the output. I haven't talked about it, but it's pretty straightforward. So let me show you that on here. So on the diagram, I usually what I do is I take a look in here and I say, okay, so this is my circuit, and I surround it with a box, and I say which ones are my inputs, which ones are my outputs, and I just pretty much do that. Okay. So let's do this here. So what inputs do I have? I have X1 and X2 and S as my input, and I have F as my output. So all I have to do is just say, well, I have an input, and it's actually X1, X2, and S, and I have one output, and the output is actually F, and that's it. I'm done with the F, with the inputs and outputs. Okay, so now I'll go ahead and just describe that circuit. So the first thing I'm going to do is I'll say, okay, well, I probably would need some sort of an S naught in here. So I'm going to use a naught. Okay, so I'm going to call it S small n. So what I'll do is I'll take, okay, here's a NOT gate, okay, and NOT gate, I basically will say NOT, and the output will be, I'm going to just call it SN, and then the input will be S. Okay, and that's pretty much it. Now, what do I have? Well, I have this gate in here. Let me call it A0, and let me call this A1. Okay, so the A0 takes, it's an AND, okay, and what does it do? Well, the AND gives me, let me just call it, for example, G1, for example, in here, and this is, or G0, and this one here is G1, okay? So I'm going to call this a G0, okay, and the inputs to this particular AND gate is going to be X1 and SN. Okay, and there's another AND gate in here, and the AND gate, the output will be G1, and the input would be X2 and S, or not AND S, just the signal S, and then eventually I'll have an OR gate, and that OR gate I can just call it O not, okay, for OR, and the OR gate will have an output F, and it will have G0 as an input and G1 as an output, or as another input, and that's pretty much it. I have done basically, I described that circuit by describing the gates. You might be wondering, why did I call them A0 or A1 or O not? Like, you'll see the gate in these primitives, they do not need me to specify these gate names, but I have the option to do that. For example, if I wanted to call this is A0 just for me so that I know which one it is, and this is A1, again, that's just for me so that I know which one it is, and this is O0, okay, just so that I know that this is the OR, okay, and now I have it. So, and this is the very basic structural representation of a multiplexer, a 2-to-1 multiplexer, and this is called gate level modeling because I went ahead and I actually just described it gate by gate. Okay, so let me just go in here and I say OpenElaborate Design just to make sure that I captured it correctly. So the OpenElaborate Design will take my code, try to interpret it, and it will just give me some sort of a diagram that represents what I just did. And it gave me that wire. And the reason it gave me that wire is the following. It gave me the wire because I'm gonna go to my sources. It's still looking at the buffer as my wire, okay? And this little tiny thing that tells me this is the top file, it's interpreting this as my file of interest. So I'm gonna right click in here and I'm gonna say this is set top file. This idea with top file will become more clear when we actually have some nesting files, but for now I'm just going to create this to be my top file, and this is the one I want to implement. I'm just going to say, hey, reload this one here. It's the same as clicking that OpenElaborate Design again. It's just going to take this one here and just interpret it as the way I want, and it's doing that. Okay, so hopefully you get to see it. It is actually exactly what I expected it to be. This is an RTL AND, this is an AND, this is an OR, and at some point there was a not here, I think, or there you go, it's here. It's this little tiny circle in here, and that's the F, and that's exactly what we did. And again, you see it's A0 and A1. You see these are the names we gave it, and this is ONA. And so sometimes it's useful to actually give it these names. So it implemented what I wanted it to. Of course, if you want to go ahead and test it on the FPGA board, you're going to have to go to the constraint file, connect X1 to some switches, the S to some switch, and the X2 to another switch, and the F to one of the LEDs or something like that. And you can go ahead and try that on your own. But for now, all I want to do is I just want to explain to you that what we did in here is a structural description of that circuit. Again, Verilog is a hardware description language, and that's really, really important. So I'm describing the hardware. I'm describing it by writing some code to describe it. That's basically what Verilog is. And because of that, because hardware is hardware, it's actually not software, as it turns out that these here, I just went ahead and I did the not at the beginning, okay? Like I'm just gonna zoom in here to show you. I did the not here, and then this one here, and then I did the and then I did another and, but who said that A0 is more important than the other A? I can, frankly speaking, do the ands like in any order I want. As it turns out, in Verilog, in this particular situation when we're talking about structure, the order of these instructions doesn't really matter because I'm describing hardware. They're actually running concurrently, and that's what makes Verilog sometimes confusing to beginners. That the order of these instructions does not matter. Okay, at least in this particular context, there are certain situations where it does. But for now, you're describing hardware. You know that X1 and X2, they're all happening at the same time. This gate and this gate, they're all running at the same time. So it doesn't matter which one comes first in terms of code. And again, if you actually save this particular file in here and you just go to the elaborate design, I'm going to say reload. It will just take my code and just interpret it one more time and just show me. And you'll see it's not going to show me anything different whatsoever. I did not do anything different. I just arranged it differently. Okay, so taking a look at that. Okay, so it's somewhere in here. So we're going to open that elaborate design, and then I'm going to say the schematics, and there you go. And nothing changed at all, actually. Okay, and one last thing before I close that in here, as it turns out that this NOT gate in here, and all of them actually outputted some signals. Okay, so I had this particular one in here, for example. I had a G0 and I had a G1 and I had the SN. They're all internal signals that you don't see them outside the box. They're actually kind of like, you don't have to define them, okay, because it's by default, because each one of them is one wire. If they were more than one wire, like buses or something, you'll have to define them. But if you wanted to, you can actually just say that they're wire G1 and wire G0 and wire, I believe it's SN, okay, and then I don't need to generate. You just do this and that's it. It's the same thing. These are already implied, and we'll talk about this later. Okay, is there a better way to do it? Absolutely, there's a better way to do it. For example, this SN in here, I don't need to use a not. I can just say, hey, just go not S in here, and now I can remove that code. You can read it on your own. It's really, I didn't do anything. I just say, well, A0 is taking the not of S. That's basically, I just implemented the not gate in here without implementing a primitive. But again, I mean, what if that circuit is a little bit bigger? I mean, this is okay. This shortcut is fine, but if it's bigger and it has like 100 AND gates or something, this method becomes really, really tedious. And as it turns out, the structural doesn't mean that we only need to describe the gates. We can actually describe it in a different method. So let me show you that. So the other method we can do is actually what we call a data flow modeling. And in a data flow modeling, we do something a little bit different. So we write the equation, for example, the one that we see in here. So like if you remember your digital logic, you can actually write this particular circuit as a Boolean, using Boolean logic as an equation. So F will be S naught X and X1 plus S and X2. It's pretty much the same thing. It just described it differently. But now instead of using gate level primitives, what I can do is I can use Verilog operators. So let me show you how we write that code to describe that. Okay. So what I'm doing now is I'm actually going in here and just describing that particular equation in here. So how do I do this? Well, I can open a new file in here just to say that I have another one. So I'm going to say another source. Okay, and another, I create a file, and then I'm going to call it, well, mux2 to 1, and then now I'm going to call it data flow, okay, just so that it's a data flow modeling. It's still structural, but it's called data flow modeling. So we're going to do this. We're going to say, okay, we're going to do that in here. And of course, you're going to have to make it a top file so that you see it. So I'm going to just go in here and I'm going to make it a top file. And then I'm going to double click in here. And frankly speaking, I have the same inputs and outputs. So what I'm going to do is I'm just going to copy this just to save some time. Okay, so I'm going to go to this one here. I'm just going to copy it. Okay, and then I'm going to do that in here, and I'll just do that. I'm just going to paste it. It has the same inputs and outputs. But now what I can do is I can say, well, F equals not S and X1 plus S and X2. I don't think it's a plus. You have to use the OR, actually, bitwise operator. So let's take a look at this table very shortly. So this table shows me all sorts of operators, and you can read it on your own. It's really not difficult. The one we're using now are actually bitwise operators, and in the bitwise operators, we have the AND, the OR, the not XOR, which is an XNOR, and it's like, this is probably the same. I'll have to take a look at the difference, but anyway, you get the idea. So you have like a not and a not, and it's like you have a not A and you have the positive A and the negative A. These are actually related to numbers. We're not using numbers now. We're just using bitwise operators in here. Okay, so that's what I did. Of course, I don't use that. I have to use that in here. But I'm getting a syntax error. As it turns out, Verilog, this type of assignment is called a continuous assignment, and the name is historic. But anyway, what it means is the following: that if there's any change on anything on the right hand side of this equation, F will change. That's continuously. So Verilog or whatever it is, it's actually continuously checking, and that comes from simulation. But anyway, what it means is that you need to use a sign here. It's not C. Again, we're using Verilog here. This looks like C, but it's not C. It's Verilog, so you're going to have to use a sign. F equals that, and then you can save that, and you can go to the OpenElaborate Design. And again, this elaborate design, you can go in here. I'm going to just reload it, and we'll see what it will be interpreting it. This is the old one, so we're going to wait for a sec, okay, till it actually interpret it correctly. Hopefully it does. Okay, so, and taking a look at it, it actually interpreted exactly as we wanted, but it gave it different names than before because we don't have control over the little tiny gates. Like this one was called an F0, this one an F0 underscore I0, and this one is an FI. It doesn't matter what it calls it. What matters is like it interpreted it correctly. It's a couple of AND gates and an OR gate. Again, what we did here is we described the structure of this circuit. Okay, we did not describe the behavior of the circuit. We physically went ahead and described the structure, and that's why we call this structural modeling. Okay, so if you're describing the structure of a circuit, we call it structural modeling.